Welcome, everybody. My name is Seth Markle. I'm here with James Bornholt today. He'll be coming out in a bit. And this is the deep dive on Amazon S3. I think we have a really interesting one this year. So just to give a little background on myself, my name is Seth Markle. I'm a senior principal engineer in an S3. I've been in S3 about 15 years. It'll be 15 years this coming February. I've worked all across the S3 stack. I've worked on our object indexing. I've worked on our disk fleet. I've worked on our front-end systems. If folks saw Matt Garman's keynote today, I worked on the S3 metadata system that we previewed today. James Bornholt, who will be out here in a bit, is a principal engineer, and he's been working on our disk fleet, and he's also been working with the open source community on connectors, including MountPoint, PyTorch, and most recently, he was involved with our S3 tables launch that we launched today. So today, we're going to be talking about using scale to our advantage and yours. So what does that mean? Well, you often have probably heard technical talks about scale, and they're usually talking about how to build for scale. So in other words, how to avoid having your software fall over when it's taking too much traffic or holding too much data, there's too much metadata. So how do you tolerate scale? But today we're going to look at scale from a different perspective. So we're not going to talk about how we design to tolerate scale, but rather how does that scale actually make S3 work better for customers? So before we begin, let's take a look at S3's scale. So here's some statistics. So S3, as folks know, is an object store, and we hold more than 400 trillion objects. That amounts to exabytes of data, and we average over 150 million requests per second. Daily, we send over 200 billion event notifications, and in total, at peak, we serve over 1 petabyte per second of traffic worldwide through our front-end fleet, 1 petabyte. So this is what we're referring to when we're talking about scale. So we're going to illustrate this concept of scale to your advantage in 3 ways today. So first, we're going to talk about the physics of data. So when we talk about physics, we talk about the real-world properties of hardware and software and how they dictate system behavior. So if any of you saw Andy Warfield's keynote right before this, you'll have heard him refer to how we think about our disk fleet as like a large thermodynamic system. We'll be talking about how those properties actually improve as our system grows. Then James will look at how the scale of S3 helps us to deliver a consistent performance and a consistent operational experience, even under real-world failure scenarios. And then we'll close out talking about how our scale allows us to design for failure in a way that actually helps us to deliver faster on your behalf. OK, so let's get into it. So we're going to talk about the physics of data. So as a software engineer, I'm often thinking about algorithmic efficiency, testing, documentation, things like that. After some of the Q developer announcements this morning, I might have to personally think about testing and documentation less often, but it's still very top of mind for me today. As a storage engineer, I'm often thinking about the real-world physical properties of the underlying hardware that can't just be solved with better software. And so we're going to walk through those physical properties, and I'm going to show how the storage system actually improves as it gets bigger. Like I said earlier, we often think about scale as how do I tolerate getting larger, but today we're going to talk about how the system actually improves because it's larger. So larger here. So S3 has grown to have tens of millions of drives, and they actually run really hot in terms of their workload. As we'll get into, there's only so much work a drive can absorb before it's at its limit. So if we can't spread that traffic across those tens of millions of drives, we're limiting what our customers can do despite having the capacity on hand to serve that traffic. But it turns out at scale, there's some pretty useful patterns that emerge that helps us to balance things out. And so we'll look at how that works. And we'll look at how that works looking at 3 actors in our system. So the first and most important actor is you, the customer. There's also the hardware in our system and the software in our system. And those 3 together will help us paint a picture of what I mean here. So let's start off talking about the physics of the hardware. OK, so here we have a hard drive. Hard drives are mechanical components that have two primary movements required to read data. So the platter spins around, as you can see in this illustration, around a central component called a spindle. You'll often hear people refer to spindles when they really mean drive count. We still have to talk about spindle counts in the system. And aside from that, there's a mechanical arm called an actuator that moves back and forth. It has a read and a write head on its tip. And it has to move back and forth to be able to access particular parts of the platter where the data resides. When you read data, you provide an address. It's really going to be an offset from 0 to the capacity of the drive. It's called a logical block address, or an LBA. And that instructs the drive on which platter and where on the platter the data lives that you want to access. And so then the actuator has to move into location. And so the actuator swings back and forth. Right? It's an actual physical component. This does not happen instantaneously. And then once it is on the right track, the odds are the data that it needs is not directly under it. And so you have to wait for a rotation to come around before the data that wants to be read exists underneath the platter. And on average, that's going to be about half a rotation, right? Because sometimes you'll have just missed it, sometimes it's right before you, so it's about a half. The act of the actuator moving is called seeking. And so the time it takes to move is called seek time. And then you have to wait for rotation. That's called rotational latency. And so these are two physical, real-world factors that cause drives to take time when you're reading data. And they're measurable amounts of time. And so this is what we mean when we say that hard drives have physical limitations. There's only so much swinging back and forth that this can do in a fixed period of time. So let's look at our software next. OK, so I won't get into too much detail here. But when you store an object in S3, we break that object apart into pieces we call shards. And we store those shards across our storage nodes, across our disk fleet, using an algorithm called erasure coding. James will actually get into more detail about erasure coding in a bit. But the important thing here is that we chunk up the data that you send us, and we store it redundantly across a set of drives. Those drives are running a piece of software called shard store. So shard store is the file system that we run on our storage node hosts. Shard store is something that we've written ourselves. There's public papers on shard store, which James will talk about in his section. But at its core, it's a log-structured file system. And so what does that mean? That means when new shards are written, we will put them sequentially with each other. If you think back to how I talked about drives working, part of the expense, part of the latency associated with using drives is that actuator moving back and forth. So by putting data next to itself on the drive, I can actually eliminate some of that cost. And so writes actually become more efficient with a log-structured file system. But from a read perspective, I don't have that luxury. I can't control when a customer wants to read which piece of data. And so I am left for reads to jump to wherever on the platter that the data happens to be. And so reads are kind of the pessimal workload where we have to pay for both the seek and the rotational latency. And so we're hopping around the drive for reads. This type of I/O is often called random I/O. Folks may have heard of that. And it usually involves a seek and then some rotation of the drive. So we have the hardware. We have the software. Let's take a look at some workloads. Storage workloads individually tend to be really, really bursty. What this means is that they're idle for really long periods of time, and then they suddenly become really demanding. A really great example of this is FINRA. So FINRA is a big customer of AWS and S3. FINRA regulates member broker-dealers and the securities markets, and they're responsible for collecting, processing, and analyzing every single transaction across equity and options markets to look for improper behavior. So it involves them ingesting hundreds of billions of records each day. I think in August, they had a peak day of 906 billion records that they processed, 2 days in a row. And on average, this is about 30 terabytes of data that they have to process in a day. And they have a strict 4-hour SLA for processing this data. And so their workload is what we refer to as bursty, because they're accessing their data really hard for a relatively short period of time, this 4-hour period I described, And then they're idle for another 20 hours a day. Not purely idle, they are ingesting new records, but they're doing all of their bulk processing in a 4-hour window. So they have 20-hour windows of relatively light activity. So let's do some math to see how many drives an example workload like FINRA's would need to be able to operate this way if you were building your own storage system. So in this example, and this, again, these are not FINRA's numbers, we have a customer that wants to hold a petabyte of data, and they want to process that data in a 1-hour period. So I'm using these numbers to illustrate the point here. So if I were to have to access a petabyte over a 1-hour period, the intended access rate is 275 gigabytes per second across that data. And if it's about a megabyte per object, that's about 1 billion objects. So it's a pretty actually reasonable sized workload. So we started talking about hard drives, and if you remember, there's two primary operations, right? There's seeking and there's the rotation. So a 7,200 RPM drive spinning around 7,200 times a minute, that works out to about 8 milliseconds per rotation. And since on average you have to do half a rotation to find your data, that's going to be 4 milliseconds for the rotational latency on your average read. A seek time on average has to move half the radius of the platter, so that's another 4 milliseconds. And remember how we talked about objects are chunked up into shards for redundant storage? Well, let's say in this example, the 1 megabyte objects are chunked up into half megabyte shards. And so to read that half megabyte, we have to scan about a half megabyte off a disk, and so let's add another 2 milliseconds for that. So in total, we get 10 milliseconds for this random read, right? So that's the seek time, the rotational latency, and the transfer time. A second has 1,000 milliseconds, and so if a read takes 10 milliseconds, then I can do about 100 reads per second. And these are half meg reads. So if I can do 100 half meg reads per second, I can do 50 megabytes per second from this drive. So the random I/O nature of this really does add a lot of overhead here. 50 megabytes a second per drive. So if we go back to the original numbers and tie this together, I have a petabyte of data that I wish to access at 275 gigabytes per second at peak. If I were just storing that data and not accessing it, I would need 50 drives if there were 20 terabytes per drive, which is the drive size that we land nowadays. But to be able to access 275 gigabytes per second at 50 megabytes per drive, I need over 5,000 drives in my system to support that workload. So there's a 100x amplification of drive count if you consider the access rate over the storage rate. And those drives end up idle 23 hours a day in this particular example, because I'm only using that capacity, that I/O capacity, for 1 hour a day. And so that's a huge amount of inefficiency. You're paying for 100x the capacity, and also you're not using it for 95% of the time. So some of you might be wondering, okay, if this is what a single workload could potentially look like, and S3 has millions of active customers, isn't this problem actually 1,000,000 times worse for S3 as a service? And this is the really cool part of operating at scale. Because individual workloads are actually really bursty, but independent workloads that have nothing to do with each other don't burst together. And so at the aggregate level, storage temperature actually becomes surprisingly predictable. Yes, younger data tends to be hot, smaller objects tend to be hot, and we have a lot of young and small objects. We have over 400 trillion objects. We also have a lot of old and large objects. And so when you layer these workloads together, suddenly the system as a whole becomes a lot more predictable. And so as we aggregate them, even though our peak demand progressively grows, the peak to mean is collapsing. And so the workloads become more predictable. And so this is actually really awesome for that physics equation that we just walked through, because we can spread customers over many more drives than their storage alone would typically require. And we can do this because the peaks for some workloads map to quiet periods for others. And so this is the first part of how our scale works to your advantage. We have tens of thousands of customers, probably some in this room, who have data spread and workloads spread across over 1 million drives each, even though their storage footprint does not require nearly that much. And there's two advantages to this. Because you're able to spread over a vast number of spindles, remember the spindles is the spinning unit of the hard drive, you're able to burst to throughputs offered in aggregate by those spindles, even though the amount of space you're taking up does not fill up the drive. And because any single customer is a very small portion of a given disk, we get that nice workload isolation we saw last slide, where peaks and valleys of different customers are decorrelated. And this is all possible precisely because we have such a massive scale. So I just spent a fair amount of time illustrating how customers are able to utilize throughput from far more drives than their data would normally require. And this predictability of workloads in aggregate is only part of the story. We still have to pay attention to how traffic distributes across the fleet so that we can prevent hot and cold spots across our disks. And this doesn't happen automatically. So objects follow some predictable patterns in aggregate, but over time, I mentioned younger data is hotter data. So if I'm writing to a drive, the data I'm writing to it's young. But then a year from now, it's less young. And 2 years from now, it's less young. And so the drives kind of cool off as they get older. And sure, deletes might come in and poke some holes in that data. And so I put more young data in there. And so it heats up a little bit, but not nearly as much as new drives. And so uncorrected, our system actually will tend towards coldness. And remember, we want to aggregate and balance the traffic across all of the spindles. It does no one any good to have a bunch of spindles that are full, but also not serving that throughput that we need. And so we could, uncorrected, end up with these pockets of high utilization and low utilization across the fleet, which isn't ideal because, like I said, we're leaving this I/O on the table. But our scale means that we have storage racks of every traffic profile in the system. And so there's actually a really large surface area for rebalancing and re-encoding when we get things wrong or when we see things cooling off. And so we do constantly move data around to balance storage temperatures across our racks and across our hard drives. And it's our chance to revisit our initial placement decisions. Maybe the bytes were hotter or colder than expected. Maybe things just cooled off because they were older. Maybe they need to be moved around for intelligent tiering. There's lots of reasons why we might want to do this. And so one useful opportunity for us to do this rebalancing is when we land new storage racks. So let's talk about storage racks just for a quick moment. So when it comes down to it, S3 is just a collection of these really massive racks of disks. If some of you saw Dave Brown's talk last night, some of the rack types we used to have weighed upwards of 4,500 pounds. That's over 2 tons. Our rack types today aren't quite that heavy, but they are thousands of pounds. They weigh more than a car. And they're actually so big that we have to consider their weight when we design our facilities, because when we land them in the loading dock, they have to be able to be wheeled to their final location without collapsing the floor along the way. And so we have reinforced flooring to support the weight of these moving around. And these are actual pictures of we call them JBODs. And you'll hear different expansions of the acronym. A JBOD, just a bunch of disks, just a bunch of drives, just a box of disks. But it's what we call our enduring term for our racks of disks. There are about 1,000 disks in these racks. At about 20 terabytes per disk, these racks hold about 20 petabytes of physical capacity each. And we're constantly landing racks like this to add more space to S3, similar to how you might buy a new drive and plug it into your laptop. But we can't just start sending all the new traffic to these drives, because like I mentioned, young data is the hot data in the system, and it would overwhelm the 1,000 spindles in the rack. Right? 1,000 sounds like a lot, but it's actually not that much when you consider 50 megabytes a second per spindle. You're not able to get that much from a rack, and so if it's all that young hot data, you'll melt down the rack. This is an artist's rendition of melting down a rack. So instead, we bring the rack online, and we start by diffusing existing S3 data onto it. This is a process we call migration. And we actually fill it to be, ballpark around 80% full of existing cooler data and allow it to mix in with the rest of the fleet. And so what this does is it frees up capacity in aggregate across the pre-existing spindles so that there's space across a lot of spindles for hot data to land, and not just all of the space in the new spindles that have landed. Because remember, we want as many spindles as possible participating in the traffic. So this provides, landing new racks provides us a great opportunity for revisiting our past placement decisions. And our scale here it becomes the powerful tool for avoiding the hotspots. Because of the scale, we have a diverse profile of racks in the system. And so there are different places for us to select different traffic profiles depending on what we need to migrate. And so the bottom line here is that storage systems are based on the physics of real-world hardware and access patterns. And so when you're running your workloads on S3, you're leveraging the scale and the physics of our system to your advantage. And so now James is going to come out and talk about how we design for decorrelation. Thanks, James.
Thank you. I'm so excited to be here. This is kind of my favorite talk at reInvent because it's a chance to talk about the really awesome work that our teams do to actually architect our systems. Hopefully also to give you some ideas of how to architect your systems, but also just some really cool stuff to talk about. So I'm actually going to pick up pretty much where Seth left off. He was telling you about kind of the benefits of spreading data across many drives, millions of drives, and how that works to your advantage. And I want to talk a little bit more about that because it's actually not a one-off. It's not the only place that we do this. And as we've been building S3, we realized it's actually kind of an architectural pattern that we use. And it's this idea of decorrelation. The idea is that we really engineer every part of S3 to decorrelate workloads. So if you have two customers running workloads, those two workloads should be decorrelated from each other. But also, even yourself as a single customer, your workload should be decorrelated from itself. And that's kind of a weird idea. Like, how do you decorrelate from yourself? So let's talk a little bit more about what that actually means. So S3 has a lot of really awesome features, right? We just launched some more this morning. But pretty fundamentally, S3 is about puts and gets, right? You put some bytes into S3, and then you come back and you get them back later. When you actually do one of these puts, we actually have a pretty important decision to make. We have to decide, when you do the put, where should we put your bytes? So here's a really simple approach to doing that. You're going to do a put, and we're going to assign you a drive, right? Here's your hard drive. Now, every time your bucket takes more puts to the same bucket, we're going to keep putting those puts on the same drive, right? We'll do this over and over and over again. Eventually, if you have enough puts, your drive will fill up. That's OK. We have more drives, right? So we'll assign you a second drive, and we'll start filling that drive up with data from your bucket. Now, you might sort of infer from the way that I'm talking about this is not how we do it, and it's not a particularly great way to do it. But I don't want to dismiss this out of hand. This actually is like a pretty good way to do allocation. And in particular, it has one key advantage, which is that it's simple, right? Simple is great. It means it's easy for us to operate. It's easy to reason about, right? It's easy to plan for. So simple is fantastic. But it does have a couple of problems. One of the problems, if you've ever thought about storage systems before, is probably pretty obvious to you, which is that you can't just store data on one drive, right? Hard drives fail. They actually fail at a fairly high rate. So of course, we have to store your data in more than one place. We'll talk more about that a little bit later on. But for now, just remember that we do store the data on more than one drive. But there are some more nuanced problems with this approach. And actually, the problems are a little bit different depending on your scale. So if you have a small bucket, right, a bucket that's not large enough to fill up a drive, it's not going to be cost efficient for us or for you to assign you an entire drive, right? Seth was talking about these drives being 20 terabytes large. If you have 100 kilobytes of data, we're not going to assign you an entire drive to yourself, right? It just doesn't make any sense. And so if you're a small customer, you're going to be contending with other customers for space, right? You're going to be sharing one of these drives and you have many different workloads running on the same drive. You get the correlation, right? You have multiple workloads trying to hit the same drive, trying to contend for the same scarce resources that Seth was telling you about, those rotations and those seeks. If you're a large customer, that's not a problem, right? You have the entire drive. You have enough data to fill up an entire drive. But now you have a different problem, which is that your performance is ultimately constrained by your storage footprint. This is the idea that Seth was telling you about, right? If I have a petabyte of data, I get 50 drives, right? That's how much space that I get. I actually might want a lot more performance that I can get out of 50 drives. These are both correlations, right? If you're a small customer, you're correlated with other customers because you're sharing a resource, you're sharing the drive. If you're a large customer, you're correlated with yourself because you're bound by your own capacity. You can't burst beyond that. So these make systems really difficult to use. They also make it very difficult for us to scale because you have to think about what if customers become unbalanced over time. So we do something a little bit different on S3. And it's actually an example of a pattern that we talk about often in AWS called shuffle sharding. The idea of shuffle sharding is actually pretty simple. It's that rather than statically assigning a workload to a drive or to any other kind of resource, a CPU, a GPU, what have you, we randomly spread workloads across the fleet, across our drives. So when you do a put, we'll pick a random set of drives to put those bytes on. Maybe we pick these two. The next time you do a put, even to the same bucket, even to the same key, doesn't even matter, right? We'll pick a different set of drives. They might overlap. We'll make a new random choice about which drives to use for that put. This is intentionally engineering decorrelation into the system, right? These objects are from the same workload. They're the same customer, the same bucket, but we're forcing them to be decorrelated. Within your bucket, that means that you're not constrained by the static resources anymore, right? So if you have a petabyte of data, you can actually be spread across many more than 1 petabyte's worth of drives. You can get the 5,500 drives that Seth was saying that you needed for your workload. If you're a small customer, you're insulated against the noisy neighbor effect. Because if you have one customer that's very hot, retrieving an object often a large number of times, that object is probably spread across a different set of drives to you, right? Even though you might overlap on one of the drives, there's other drives you can go to that also have the data. So we get to decorrelate you from the hot workloads you're contending with. So this idea of shuffle sharding is actually really cool. And it's actually pretty fundamental to how the team thinks about S3's resources. Our mental model for this, really, is that when we talk about S3 being elastic, what we mean is that any workload should be able to burst to use every drive in our fleet, the tens of millions of drives that we have, as long as they're not interfering with each other. So that means if you're FINRA, you can burst to that 1 hour a day to get terabytes per second of bandwidth if you have to, far beyond what your storage footprint, your capacity, might otherwise allow you to have. So software sharding is really a powerful mechanism for sharing resources efficiently and intentionally creating decorrelation between workloads. Once you know this idea of shuffle sharding, it actually starts to pop up all over the place. It's not just drives. So let me give you another example of shuffle sharding in S3. Let's talk a little bit about DNS. When you send a request to S3, you might know that you're actually sending a request to this DNS address, right? Your bucket name .s3.amazonaws.com or something else if you're in a different region. When you actually go and resolve one of these names, you get back a list of IPs. You actually used to get back one IP. A really cool launch we had last year was to add multi-answer DNS support to S3. So now when you do one of these lookups, you actually get back 8 IPs. So why does this matter? Why am I telling you about all these IPs? Well, each of these IPs points to a different set of servers in our fleet. And this is how S3 does load balancing, right? When you do a DNS lookup, that's when we decide where we think we should send your requests. And it's probably going to be different to some other customer. This has a couple of advantages for you. The first one is that as a single customer, it's great, because again, you can spread your requests across many hosts, right? Across many of these servers. This minimizes the effect of hotspotting, right? If you're sharing one of those servers with other customers. But it also means you can burst to much larger amounts of bandwidth than you might otherwise get if you only had one place to go for your data. There's also shuffle sharding going on here, right? If Seth and I do a DNS resolution for the same host at the same time, the same bucket name, we're actually going to get back different sets of front-end hosts, different sets of IPs. And so what that means is that even if one of us is a very hot customer, even if we're sending a lot of traffic to whatever IPs we got back from that DNS resolution, we're not going to contend with each other, because we're almost certainly going to a different set of hosts. Now, importantly, we engineer these front-end hosts, these IPs that you get back, to be stateless, right? So it doesn't matter which one you send requests to. You'll be able to access all the bytes, all those random drives we gave you, no matter which server you go to. So again, it's that idea of decorrelation. DNS shuffle sharding is actually especially important for fault tolerance. So we have a lot of these servers, as I was saying, and sometimes servers fail, right? That's a totally normal thing. If there was some correlation between which servers you could use to access your data, this wouldn't be great for you, right? Because if one of these servers failed, it'd be kind of like a systematic failure in your bucket. You wouldn't be able to access those bytes anymore. So the statelessness lets us limit the impact of one of these failures. These kinds of failures are also why retries are so important, right? A single failure will almost always succeed the second time, right? Because it'll almost always go to a different host. All the AWS SDKs automatically implement retries for exactly this reason, right? We want to make sure that if one of these hosts fails, you go somewhere else. And in fact, the SDKs are actually pretty smart about this. It's not just like, if it fails, try again. They're actually a little bit smarter than that, because they know what kinds of request failures, what kinds of HTTP error codes you get back correspond to server issues, right? They know the difference between a 403, an authentication problem, and an actual server error. And so when this happens, they can actually intelligently steer the retry to a different host. They can forget about the one that was failing and deliberately send a request to a different IP. And again, they can do this because of the statelessness, right? Because it doesn't matter which host they go to for any particular request. Your buckets aren't mapped to specific servers. So the bottom line here is that shuffle sharding is just like an awesome way to engineer for decorrelation. We do it across S3. We do it on the client SDKs. We do it on our front-end servers. We do it on the drives. Decorrelation is how we give you resilience and stability. It's also a thing that's only possible because of the scale that we're working at. So shuffle sharding is a great technique. One other thing I want to tell you about shuffle sharding. It's a little bit in the weeds, but when the team told me about it, it was so awesome that I couldn't help but talk about it. So the AWS Common Runtime is a low-level software library that we use for working with S3. It implements all of S3's best practices, things like retries, automatic parallelization of requests, everything you need to get really high throughput out of S3. Hundreds of gigabits of throughput from a single host. Now, most customers will never interact with the CRT directly, right? They'll get it either from the Java SDK or the Python SDK, which include it as libraries, or using some of our open source connectors, things like MountPoint for S3. Now, the CRT does one really awesome thing to take advantage of shuffle sharding, not just to give you fault tolerance, like all our SDKs do, but actually to improve performance when you talk to S3. And it goes like this. This is a graph of request latencies to S3. Right? So I have latency on the x-axis and a distribution of the latencies on the y-axis. Most of these requests are pretty fast. But you can probably see down the end there's like a few outliers. Right? There's a few pretty slow requests. That happens in a distributed system. That's totally normal. Right? The CRT does a really cool thing with this. The CRT actually dynamically tracks this distribution. And what it's doing is it's tracking to keep a live estimate of the tail latency of the requests that you're making. So let's say that it's tracking the P95, the 95th percentile of the latencies that you're getting back from S3. Once it knows this, the CRT starts doing kind of an interesting thing. It starts intentionally canceling requests. Right? Requests that go past this P95, requests that are slower than this P95, the CRT cancels them and retries them. Now, on the surface, that might seem kind of surprising. Right? Why would you cancel a request, especially a slow request? It's probably pretty close to responding. It seems like you're throwing away work. But actually, shuffle sharding is what makes this work. Right? The new request that you send is probably going to go to a different front-end host. Right? It's probably going to go to a different set of drives because they're spreading your requests across multiple drives. And so actually, it's very likely that that retry will go quite fast. And so you end up with a distribution that kind of looks like this. Right? The left-hand side is still the same. Right? The left-hand side hasn't really changed. But everything past that P95, where we started canceling and retrying requests, we've pulled in all the tail latency. Right? Most of those requests became very fast on the retry. And so we've pulled in the tail latency distribution. Now, to be clear, right, this is gambling. Right? We're taking a bet that that request will be faster the second time around, and it's not always going to pay off. But in practice, it's a ridiculously effective technique to get not just fault tolerance out of shuffle sharding, but performance as well. So shuffle sharding is kind of everywhere. Awesome design pattern. Let me tell you a little bit about how this actually works. Right? So we like shuffle sharding. We like the idea of kind of spreading data across the fleet, as many drives as we possibly can. But how do we actually do it? Right? When you do one of these puts, we have to pick a set of drives. We have to decide this drive, and this drive are going to be the drives that you put your bytes on. How do we make that decision? Well, one thing we could do is just to look at all the drives. Right? Look at every drive, figure out what the optimal set of drives is for you. Right? Maybe it's the least full drives or the least contended drives. We can make an intelligent decision by looking at all of our drives when you do a put. Unfortunately, we have a lot of drives, like a lot of drives. Right? And so we can't actually look at all of them. We have tens of millions of drives. We can't look at all of these tens of millions of drives for every put that we do. Because actually, there's not just one put, right? We're doing many millions of requests per second in S3. There's many millions of puts all trying to make this calculation at the same time. There's also a little bit of a coordination problem here, right? If we're all looking at this data at the same time, how do we know that we're all making the right decision? So we can't do this perfectly. What about totally randomly? Totally randomly is actually a good strategy, right? Don't even try to get it right. Just pick a drive totally at random and put the bytes there. That actually works quite well, and is like in the spirit of shuffle sharding, is a really effective technique. There is a problem with doing this randomly, though. Let me show you what I mean. What I'm going to show you is a simulation of the capacity usage, the amount of space that we use on a drive. So here's a graph, right? On the x-axis is actually a percentage, right? And it's how balanced the capacity there. So over our fleet of drives, if you do total random allocation, so you do a put, you totally randomly choose what set of drives you get, what this graph is showing you is the distribution of the capacity usage, right? How balanced the capacity usage is. And so what you see in this graph is that actually, if we did this totally randomly, then over time, we end up in a place where some of our drives are up to sort of 10% less full than other drives, maybe even up to 20% less full than other drives. And this isn't great, right? It means we're wasting a bunch of capacity because we're making these random choices. We're not actually thinking about, well, which drive is the most full? We shouldn't put more data there. Which drive is the least full? That'd be a good place to put data. So totally randomly is OK, but it risks this imbalance, and imbalance is ultimately a cost problem, right? It means that we have to buy spare capacity to make up for this imbalance. So let me tell you about another really cool magic trick. It's called the power of two random choices. And here's the idea. If you're trying to optimize a metric, so here we're trying to optimize for capacity usage, right? Instead of doing it totally at random, do a very different thing, or a very slightly different thing. Pick two drives, right? Not just all of them, just pick two random drives, and look at them and figure out which one is least used, and use that one, right? So don't look at all the drives. You don't need to look at all tens of millions of drives. Pick two drives totally at random. Whichever one is less full, use that drive. Now, this doesn't seem like you've gained much, right? Why would picking two random drives help you, right? There's tens of millions of drives. But actually, it turns out to be incredibly effective, right? So this is the distribution of capacity when we use that technique. So rather than just totally randomly making choices, randomly pick two drives, or 10 drives, or 20 drives. Doesn't actually super matter, right? Pick two drives and use whichever one is better, right? On whatever metric you're trying to optimize for. So here we're optimizing for capacity. This is the distribution you get. It's ridiculously better. So this is a really dramatic effect, right? You're kind of getting the best of both worlds. You're getting the very, very close to perfect, right? Kind of almost as good as you could do by looking at all the drives every time. But you're getting the performance, the efficiency, the lack of coordination of randomness by just looking at a couple of drives. In other words, just a little bit of knowledge about the system, just looking at two drives, is enough to go a long way to making your placement better. So power of two random choices is super awesome. It's a pattern to look for any system. It's actually really, really fun. And it's techniques like this that make it possible for us to do shuffle sharding at scale, right, and make it effective. So we engineer intentionally to create decorrelation across the entire S3 stack, not just our drives, not just our front end, the whole thing. We do this with shuffle sharding, right? We intentionally place data into different streams so that it doesn't interfere with each other in the future. And then we use algorithms like the power of two random choices to get scale and fault tolerance without paying performance cost. There's a really cool article on the Amazon Builders Library about shuffle sharding, if you want to check that out. Many of the same ideas, more pictures. It's pretty great. And I really encourage you to look for ideas to do shuffle sharding and opportunities to do shuffle sharding in your systems. It's a low-cost way to engineer resilience and can often be very, very simple to implement. OK, so we've talked about correlation and the idea of engineering for decorrelation. The last thing I want to tell you a little bit about is how we engineer for velocity. And one of the really surprising things that I've learned while working on S3 is that actually all the work we do in designing for fault tolerance turns out to actually be very helpful to help our teams move faster and deliver things faster. So let's talk about what that actually means. Obviously, at scale, failures are a fact of life, right? Drives fail all the time, kind of randomly, right? This is ultimately a distributed systems problem, and every distributed system has this problem. Things fail. It's not just drives. Right? And it's actually important to be precise about failure when we talk about failure. Of course, drives fail individually. Right? We see failures of hard drives. We see failures of racks. But there are often hardware issues. Right? There are often things like a fan is broken or a cable is broken or something like that. But we also engineer for larger fault domains, right? Not just drives. And in particular, S3 storage classes that use multiple availability zones are resilient to the permanent loss of an entire data center. Right? So one of these availability zones can go away forever, and all your data is still intact. Right? Now, we've done entire reinvent talks about how we make this happen. It's not easy. Right? It's not just about architecture. Right? It's not just about having redundancy in the system. Fault tolerance at this scale is actually as much about engineering culture and how teams think about the system as it is about actually just knowing what the failures are in the first place. The other really important thing to know about fault tolerance is that it's not just about being robust. It's not just about, like, oh, we'll have some redundancy and everything is great. It's not just about the shape of our systems. One of the hardest and most subtle problems in dealing with fault tolerance is actually knowing when something has failed in the first place, which sounds crazy, right? But actually, how do you know the system has failed is a surprisingly hard question to answer at our scale. And so as an example of this, one of the things that S3 is doing all the time, we are constantly scanning every single byte that we store on all of our millions of hard drives to check its integrity, right? To make sure that it's still there, where we expected it to be, and that it's intact. if you were to make a list of our largest customers, right, the customers who send us the most requests per second, this scanning work, this background scanning work to find which data is intact or if any data is missing, would be very high on that list. So we do this a lot. We also take it very seriously from an operational perspective. We have alarms on the P100 longest time, the most time a byte has gone without being scanned by this process, right? We will page and wake up engineers in the middle of the night if our metric goes too high. We really do care at making sure that every single byte in our fleet has been scanned at some regularity. But none of this should be too surprising, right? Fault tolerance is the thing that we do all the time in S3. Let me talk to you a little bit about how we get there, right? How do you get fault tolerance in this world? And it's an idea that we call erasure coding, right? So here's a really simple way that you could do this. If you want to get durability, you want to get resilience to single drive failures, one thing you could do is to replicate your object, right? We could put the object onto multiple drives. So here's a 1 meg object, and I could make copies of it, right? I can make, let's say, 2 copies, store them on different drives. Now I'm resilient to drive failures, right? If 1 drive fails, I've still got 2 copies. If 2 drives fail, I've still got 1 copy. So I can survive some drive failures in this world. We can actually get resilience also to that entire availability zone failure model by putting these copies in different availability zones, right? So now if one of the availability zones fails, the other 2 still have a copy of the data. We can still get the object back. Now, again, there's a lot to like about replication, right? And in particular, it's another one of those things that's very simple, and we like simple, right? We do use replication in our system. It just has one downside, and the downside is that it's very expensive. Right? To store 1 byte of customer data in this model, we now have to store 3 physical bytes. We have a 3x amplification on the bytes that we're storing to get this fault tolerance. Now, in reality, to get to the 11 nines of durability that we design S3 for, you actually need more than 3 copies. So it's even worse than it looks on the slide. So what can we do instead? I love talking about erasure coding. It's my chance to talk to you about some really cool math that we really enjoy working with in S3. Here's the idea. I want to start again with my 1 meg object. I'm going to divide it into 5 pieces. Now, so far I haven't gained anything, right? I've just got like the same object but split into 5 chunks, right? We call these shards. Here's the trick. We do some really fancy math to compute some extra shards called parity shards. Now, these aren't just any shards. They have a pretty interesting property. The math that we do to compute these shards gives us a property that any 5 of these shards is enough to recover the original object. So obviously, if I just looked at the top 5, right, the original data that I split up into 5 shards, I can get the object back. I just glue it back together, right? That's super simple. But I could also do it in a different way, right? I could take, let's say, 2 of the parity shards and 3 of the original shards, and I'll be able to get back the entire original object. And it doesn't actually matter which combination I use. Any combination of 5 of these 9 shards will be enough to get back the entire object. And so now, if I spread these shards across multiple drives, I'm getting fault tolerance. Right? Some number of those drives can still fail, and we'll be able to recover the original object. And again, importantly, it doesn't matter which drives. Right? Here, any 4 drives can fail, and we'll be OK. We'll still be able to recover the object. This erasure coding, again, also works to give us tolerance to availability zone failures. Right? We just have to spread the shards across the availability zones. So here, the math works out kind of nicely. Right? I have 9 shards on the slide. We have 3 availability zones in most regions. So I put 3 shards in each AZ. And then even if an availability zone fails, I've still got 6 shards, right? I've still got enough shards to recover the object. Doesn't matter which shards were lost. The magic part of this is that the overhead is much lower than it was for replication, right? In the version that I've drawn on the slides here, we can tolerate losing any 4 drives, right? To get that with replication, I would have had to store 5 copies, right? The 4 that are going to fail, and then 1 extra copy to still have the object. So I would have had a 5x overhead. Right? I would have had to store 5 physical bytes for every logical byte that I wanted to store. With erasure coding, we created 4 parity shards. Each one of those parity shards was as large as one of the 5 shards of the original object. And so we ended up with only an 80% overhead, right? 1.8 physical bytes for every logical byte that we wanted to store. So erasure coding is actually like super magical math. It's a lot deeper than I'm going to go into and explain here. But what it gets us is fault tolerance at low overhead. So it's really cool. But you've probably heard about erasure coding before, right? It's actually a pretty common storage technique. It's kind of table stakes for a storage system. What I actually want to tell you about is some of the ideas of erasure coding that go beyond just fault tolerance, right? So 2 examples that I want to talk about in particular. The first thing I want to tell you about is that erasure coding actually is a really powerful mechanism for development velocity. Because I've been telling you about different kinds of failure domains, right? I've been telling you about how drives can fail, racks can fail, availability zones can fail. Our systems are designed to tolerate those failures using techniques like erasure coding. But once you've engineered for failures like these, the cause of the failure doesn't actually matter very much, right? If a single drive fails because a cable is broken on the drive, that's the same thing as if a single drive fails because there's a bug in the software running on the drive, right? It's the same impact to the system. And so actually, we can use our fault tolerance to be able to deploy things faster and gain confidence in changes faster. Maybe we start by deploying a new piece of software on just a single host or just a single rack. Maybe we get a new hard drive type, and we deploy that just with 1 drive or 10 drives or 100 drives, right? A very small footprint of that capacity to start with. That way, only a very small piece of the data that we store in S3 will be exposed to that new fault domain. So if it turns out that the software doesn't work or the hard drive has a problem with it, that's OK. Right? It's a very small fragment of our capacity. Our fault tolerance means that we can tolerate that drive going away or that piece of software going away. In other words, we get to deploy new software and new hardware with the expectation that it will fail. Now, this doesn't absolve us from thinking about durability and making sure that systems are bug-free. Our teams are extremely careful about new components. So in practice, these failures are rare. But being pessimistic like this helps us. It helps the teams to deploy new ideas with confidence. They don't get paralyzed thinking about, well, what if this one drive fails? It's OK for one drive to fail. This kind of production experience, getting systems into production as quickly as we can, is invaluable to distributing and to developing S3. Right? Because even if we only allow, let's say, one of these shards to be exposed to new hardware, to new hardware or to new software, at our scale, that means being exposed to exabytes of data, to millions of requests per second. And we can get that experience without any risk to the durability of our data. So fault tolerance gives us velocity, helps us to deploy things more quickly. This all sounds great. There's one catch. You might have noticed earlier that I was telling you about shuffle sharding, right? And the idea that actually we're going to put objects randomly across all the drives. While there are very few of these new platforms in a fleet, maybe 100 drives, right, out of the tens of millions that we have, or maybe 1 rack of servers that have the new software, the probability that your object is exposed to that capacity is very low, right? When you do a put of one object, we pick some drives, very unlikely that those drives are going to contain the new software or the new hardware, right? But there's another little pesky bit of math here that you might have heard of called the birthday paradox. The idea of the birthday paradox is that in this room, it's actually pretty unlikely that someone shares my birthday. I'm not going to try to find out because I don't want to tell you what my birthday is. But it's pretty unlikely that someone has my birthday. But if you looked at the entire room, the chance that there exists 2 people in this room that share a birthday is very, very high, right? In fact, a room this large is 100%. It's a pigeonhole principle, right? So the birthday paradox tells us that even if one object is very unlikely to be exposed to a fault domain in this case, very unlikely to get unlucky and be chosen to have these drives, at scale, there's going to be at least one object that gets overly exposed. So most objects might only have, let's say, 1 shard on the new drive or 1 shard on the new software. But there's going to be one object somewhere in our system that got super unlucky and just happened to be assigned to, let's say, 5 of them, right? 5 of the 100 new drives in our fleet. Just a question of math. And so now we actually have to be a little bit more careful, right? We can't just totally randomly spread shards across the fleet anymore. Our shuffle sharding system actually intentionally incorporates knowledge of these new failure domains, right? It knows about new software and new hardware, and it is intentionally making sure that when it picks a new random assignment, when it does the shuffle sharding, right, it limits itself to only putting 1 shard on that new hardware. An example of this kind of idea, this idea of sort of shuffle sharding with a guardrail, is something called the shard store system that Seth was telling you about. This is our newest storage node software. It's the software that runs on all of our drives. We've actually been rolling this software out over the past few years across S3. And using erasure coding made this possible and made it safe at every step. Because we started with shard store by just allowing 1 shard of an object to be stored on one of these shard stores, these new pieces of software. And we left it like that for a while. The team learned a bunch about the data they got from that experience. They tuned shard store, they improved shard store, and then we raised it to 2 shards, right? Then we raised it to 3 shards. Then we raised it to an entire availability zone worth of data. And then eventually we can remove the guardrail and shard stores everywhere. We were able to change the engine of S3 without you even noticing, right? We've rebuilt this most fundamental part of our system, and we use erasure coding to make that happen. One more thing about erasure coding and how, again, it's not just for fault tolerance. Erasure coding is actually a great lever for increasing performance as well. And the idea is actually pretty similar to the thing I was showing you a moment ago about the CRT, the common runtime, and how it cancels requests and retries them. Because remember, if I have one of these erasure coded objects, I need 5 shards to recover the object, but it doesn't matter which 5, right? And so I can pick 5 of these shards, and if it turns out that actually one of these shards is slow for some reason, maybe the drive is overloaded because you're contending with other customers, that's okay. We can just go and pick another one, right? We can cancel that request because it was going too slowly and try a different shard, right? Reading an extra shard using shuffle sharding helps us to hedge against tail latency that comes from the slowest shard. So again, fault tolerance is more than just fault tolerance. It's also for velocity. It's also for performance. It's actually kind of cool. The bottom line here is that the S3 team spends a lot of time planning for fault tolerance, right? It's not just about having redundancy in the system. We work really hard to make sure that we can detect failures, respond to failures quickly, and we design redundancy schemes like erasure coding around the ability to do this kind of thing, to detect failures and to recover from them. As an engineer, being fault tolerant sometimes feels like a bit of a burden, right? It would be so much easier to build systems that they just didn't fail, but they do. At scale, being fault tolerant is actually a huge enabler, right? Our teams can move quickly, they can move with confidence, exactly because our systems are resilient to failure. So that's pretty much all I wanted to tell you about today. I hope this is giving you a little bit of a glimpse of how we think about building a durable, elastic storage system and how S3's scale works to our advantage and ultimately to your advantage as well. As always with our storage teams, the tenet that we live by is that we are happiest if you are never thinking about us, right? Our storage systems should just work. And you shouldn't have to think about S3 or anything like that. Hopefully I've given you a sense of how our teams bring that idea to life, right? Maybe I've given you a few ideas that you can take home. You'd be surprised how often opportunities for shuffle sharding or the power of 2 random choices actually show up in systems when you start looking for them. Or if you even got none of that, I hope you really enjoyed geeking out with us a little bit about some of the cool things we do with S3. Thanks so much for being here today. Enjoy the rest of the reading.